Welcome to the first lecture on module 9. In module 9, we are going to discuss on radiation heat transfer, and in the first lecture of this module 9, we are going to discuss on introduction to radiation heat transfer. In this lecture, we will try to discuss some basic concepts and we will introduce with all these concepts of radiation. Now, to start with, that we understand, and in fact, we have discussed in our introductory section that radiation is the another mode of heat transport operation, and in this mode of heat transport operation the requirement of the medium is not there. So, medium is not necessary for this radiation heat transfer, and radiation heat transfer is also very important from a chemical engineering point of view, because radiation heat transfer particularly important is important when we have high temperature operations. For example, when we are considering about the furnace, we are considering about that kilns, and when we are considering about that say heating at very high temperature. So, this when the temperature difference between the system and the surrounding, or the energy exchange between two bodies, when the temperature difference is very high, then the radiational exchange becomes very significant, very important. Otherwise, in normal situation, when the temperature is very low, normally say 20 degree, 30 degree, 40 degree centigrade, 50 degree centigrade, and these temperatures, and when the one is at 50 degree, another one is at normal temperature 25 degree or 30 degree centigrade, the exchange, radiational exchange is not that much sufficiently important, but when the temperature is when the temperature difference is large, then particularly that happens when the surface temperature of furnace and the environment temperature. Furnace temperature could be as high as 800 degree centigrade, 1000 degree centigrade, and so on. And then that atmospheric temperature is 30 degree centigrade. So, the exchange becomes very important, and then the radiation becomes very significant important. Okay. So, radiation heat transfer is that way is one important area of heat exchange where we have to be very much familiar with this, and to avoid any much loss of energy due to radiation is very important. And we know that solar radiation is one important radiation that we utilize for our day to day utilities, day to day usefulness. Now, in this case, in this lecture, particularly when we are considering about the heat transfer, we will be discussing on thermal radiation part. And we know that that thermal radiation is an electromagnetic radiation. This is also an electromagnetic radiation. Electromagnetic radiation, this is emitted by a body as a result of its temperature. Okay. So, that's we can say that all bodies around us, they emit thermal radiation. Okay. And the intensity, of radiation, that varies, is function of temperature and the surface characteristics. Okay. Characteristics of the body. Okay. Now, so what happens is that a body cannot emit any radiation, thermal radiation, when it is at absolute 0. So, that means all bodies around us emit thermal radiations above absolute 0 temperature. So, now that as we understand that because that temperature is important. So, more and more temperature that thermal radiation becomes more and more important. Now, if we know that regardless of the type of radiation, so we can have a different type of radiations that we will see just the spectrum, that we can have thermal radiation, we can have infrared radiation, ultraviolet radiation and so on. So, regardless of type of radiation, we can say that the radiation moves with a speed of light, and that is say c equals to 3 into 10 to the power 8 meter per second, where speed of light, and this is c is again given as nu into lambda, and where nu is called your frequency. Okay. Nu is called frequency and lambda is called wavelength. Okay. And we know that emission of radiation from a body is not continuous, but it occurs because we understand that that it is also a wave. So, wave has got particle property and a wave property. So, thermal wave is also have particle property and wave property, and emission of radiation from a body is not continuous, but occurs in the form of discrete quanta. Okay, this is based on the quantum mechanics, with or having energy equals to E is equal to h into nu. So, h is called Planck constant and nu is called the frequency. H is called Planck's constant and this value is 6.6256 into 10 to the power minus 34 joule second. This is the Planck's constant. So, and nu is called the this is nu is called the frequency of radiation. So, we can say that higher the wavelength, frequency is inverse of wavelength, is equal to lower the frequency equals to lower the energy of radiation, and vice versa. Okay. So, that we understand, that means lower the wavelength, higher will be the frequency of radiation and higher will be the energy of radiation. Okay. Now, if we see that this is a figure that says that the electromagnetic spectrum, it gives that how what are the radiations in different regions. This is very clearly being shown over here. We can see that our point of interest is this thermal radiation, this is our point of interest, but there can be different type of radiations. This is starting from, and as you see that in the right hand side it is this lambda mu. So, it is the wavelength of the radiation is increasing and frequency is decreasing, and in the left hand side the frequency is increasing, but the wavelength is decreasing. Though these rays have got high energy because they have low very high frequency like cosmic rays, gamma rays, okay, X rays, they have high energy radiations. Ultraviolet rays also much lower, but still on the higher side, and this is that in the thermal radiation we can see that the visible range is very small area, very small narrow range of radiation that comes under the visible range, and therefore which is in the coming in the thermal radiation, and for small range of these we find the different colors. We see that we know that VIBG or violet, indigo, blue, green, yellow, orange and red. These are the different distributions of color. So, when they are mixed up, then it is looking like a white color, but when they splits into different regions, the white color is different, it splits into different frequencies, then we get the different color spectrum. And we can see that V, we know already that V is the violet, which is of higher frequency color, and red, R is the red, which is of low frequency color. That means high energy color is violet and low energy color is red. And we see that a very small range of spectrum, very small range of frequency or wavelength, the thermal radiation, and particularly again the visible radiation is involved. And then in this side we are getting the infrared radiation, then microwave, TV radar, FM broadcast, and ultrasonic radiations are coming in the much higher wavelength and much lower frequency region. And we know that the thermal radiation, this range, as we can see from here, this is 0.1. So, it is basically 0.1 to 10 to the power 2, that is what we find in micrometer, that is the thermal end. But in the visible, this variation is 0.35 to 0.75 micrometer. So, only very narrow range of the wavelength is involved in case of thermal radiation, and that too in the visible region. Okay. Now, after this a brief idea about the different types of spectrum and different types of radiations, and particularly our interest is in for in this very narrow range of that particularly thermal radiation, and that too sometimes we may be interested for the visible range. Okay. Now, let us further see some basic concepts like typically we can say that reflection, absorption, and transmittance. So, these are the three phenomena that do happen when light falls on a body. So, if I consider a body on which the light is incident, so this is suppose the incident radiation. It can be light, it can be energy. So, for our case it is the thermal energy we are more considering about. So, incident radiation, so thermal radiation, and then that part of this is getting absorbed, part of this may get reflected, and part of this may get transmitted here. So, therefore, there could be three terminologies. One is called absorptivity, reflectivity, and transmittivity. So, what is the absorptivity? The fraction of that, from the name itself we can understand that absorptivity we also tell as alpha, reflectivity we say as rho, and transmittivity we say as tau. So, we can say that alpha absorptivity is nothing but a fraction of energy. This is the fraction of incident radiation absorbed by the body, So, this is the fractional energy, and then reflectivity similarly the fraction of incident radiation that is reflected by the body. So, it is the fraction of incident radiation reflected by the body, and transmitted is the fraction of incident radiation transmitted by the body. So, what we find that summation of all the three fractions should give you the totality, the whole, that means whole amount of incidence, whole amount of incident radiation. Therefore, we can say that alpha plus rho plus tau, and that is equal to 1. So, this is called 1.0, this is the totality. Now, so there is absorptivity plus transmittivity, reflectivity plus transmittivity of a body, sum of all these three together is basically equal to 1. Now, the question is that we know that a particular substance may not have transmittivity, a particular substance may not have reflectivity, a particular substance may not have much absorptivity. For example, if we see that glass, if we try to see for glass, so what is there for glass? We know that glass is normally transparent glass. If we say it is transmittivity is high, high transmittivity. So, for glass we have high tau and also we can say high rho, high tau and rho, but very low alpha. Okay. Similarly, we can have say typically say a gaseous medium, and for gaseous medium we know that absorptivity is high, high absorptivity, and then okay, and moderate, we can say that moderate transmittivity tau, but low reflectivity. So, this is what is the for gaseous medium. Similarly, if we say that metal plate, if we say metal plate, okay, so this is the case. In case of metal plate, absorptivity and reflectivity is high, it can have high absorptivity alpha, high reflectivity also, but no transmittivity or poor. So, that is what is happening. So, depending upon the composition of the material, that means the nature of the material and its of the body, material of constitution of the body and the surface characteristics, that all these properties depend. So, alpha, rho and tau, these are dependent on materials of constitution of the body and material of constitution of the body and the surface characteristics, because surface is very important here. Now, we will see that the reflectivity now can be defined into two parts, okay, or the reflection, it has got two components, it can be divided into two parts. One is called specular reflection, another is called diffuse reflection. Okay. So, what is specular? From the if we see that this is the surface and this is the normal to the surface and this is the incident radiation and this is the reflected radiation. So, this is theta 1 and theta 2, okay, and this is called specular. So, theta 1 is equal to theta 2, this is specular. So, it follows the law of reflection is followed. So, we can say that specular reflection is a type of reflection which follows the law of reflection, and incident radiation is reflected with an angle equal to the angle of incidence. So, theta 1 is the angle of incidence, theta 2 is the angle of reflection. So, angle of incidence and angle of reflections are same. This is called law of reflection, and that is being followed by a specular reflection method. And specular reflection, this takes place, as we can understand, for smooth surfaces. I am sorry. This takes place for smooth surfaces. Typical example is glass. Okay. Now, diffuse reflection, if we see that this is the surface. So, if this is the normal to the surface, okay, this I say normal, and this is the incident radiation. It is coming with an angle say theta, but reflection can happen in any of the directions. This can happen in any other directions. Then it is called a diffuse reflection. So, it does not go by any particular direction, it can happen to any of the direction in this region. So, in this region of 180 degree, 0 to 180 degree, any of the angles with these things, it can happen with the normal, it can happen, and therefore, this is called diffuse reflection, and this is normally happens, this does happen with rough surfaces. So, they do show this kind of behavior, and we normally in practice we will see that when we will tell about this radiations, it is basically a diffuse radiation is important, that is what we are going to discuss. Okay. Now, one point I should say here, that we just see the color of a body, that usually we know, but still for just understanding that when we say about the color of a body is blue, or color of a body is say green, or this color of this ink is black, whatever the ink I am writing is say black, what does it mean? It means that ink material, this absorbs all other radiations of the visible region except that black, when you say black, it does not say anything. Black means it color of this ink is black, means this usually that the ink material that absorbs all the wavelengths of the visible region. Now, color of the ink is blue, means that that ink material that absorbs all the radiations of the visible region except the blue radiation, and the blue wave, and this blue the frequency of this wave, or that wave corresponding to blue color, that is getting radiated, or that is getting emitted by this ink material, and therefore, we see the color. So, when the light falls on this particular substance, all other frequencies are getting absorbed except the frequency related to blue color, then we find the blue color for the ink. When we find black color, means all the visible range colors are getting, frequencies are getting absorbed by this material, and therefore, we are seeing it to be black color. And when we say that white color, then we find that all the radiations of related to all the frequency visible range, they are getting emitted or radiated, and therefore, we cannot distinguish any color whether it is a blue or red or green. Okay. Now, this is regarding, now what we will say is that, so for black surface we can say, for black surface we know that rho equals to 0, that means there is no reflectivity, tau is equal to 0, there is no transmittivity, but alpha is equal to 1, and for opaque white surface we know that rho equals to 1 opaque. So, reflectivity is there, but no transmittivity is there. So, tau equal to 0 and alpha is equal to 0, and as I told you that in case of diffuse, that all the incident radiations are reflected in all the directions uniformly, and that the reflection is called diffuse reflection. And what happens is that we can understand that from the concepts that no real surface is either specular or diffuse surface. Okay. And now, another property of a surface is that it emits the radiation. So, emission of radiation is a property of the surface. Okay. Now, we can say that emission with respect to there is a terminology is called emissivity. Okay. So, this gives that how good, this is a measure of how good the surface emits the radiation. Okay. So, for perfect emitter, so its range will be 0 to 1, and usually 0 is normally not being seen, but 1, yes, 1 means it is perfectly emitting all the energies incident on it, or it emits, it is a perfect emitter of radiation. Okay. Now, we will see that, and that is normally called a black body. For black body, epsilon, that is the emissivity, is equal to 1 and 1.0. So, that means that depending on the surface temperature, the emissive power or the amount of energy that is being emitted by the surface is there, and all the surfaces we have discussed, all the surface they do emit some amount of energy. All the surface they do emit some amount of energy when the temperature is absolute 0, and it is expected that the black body, so basically that the emissivity and emissive power, there is a datum, and data means upper ceiling of the emissive power is being given by the black body. So, it is a black body who is supposed to emit maximum radiation at a particular temperature, and therefore, the emissivity or emission power of the black body is very high or the highest, and it is equal to 1. So, that is the upper ceiling, and any other real bodies which at the similar temperature they will have emissivity much lower or lower depending upon the type of surface structure, and it will be always less than 1. Okay. Now, if we see that in general, what happens is that all the fundamental laws and relations for radiation are being based on or developed for surfaces on the basis of a concept of a black body. So, we will discuss now for a black body radiation. Black body radiation, it discusses that the fundamental laws and relations for radiation, okay, are developed for surfaces of the concept of a black body. So, that means a concept has been taken which is the ideal, and then rest of the things will be approaching towards the ideal case, as I told you, like emissivity, that a surface which is a black surface, it is being designated that it will emit 100%, that means 1, whatever its emissive power, that will be 1, that is basically that emissivity is 1. So, all other surfaces will have emissivity lower than that, and it will be a fraction which will be less than 1. So, now what are the properties of a black body? So, properties of a black body, what should be the properties? Because the black body is a very important thing for a radiation concept. So, the properties are that a black body completely absorbs okay, the incident radiation. That means it absorbs everything irrespective of wavelength. That means, and it doesn't reflect any radiation and of visible range, because we can say only of visible range. That means what? We have told already that alpha absorptivity equal to 1, but it does not go for any kind of reflection. So, rho is equal to 0, and it does not go for any kind of transmittance. So, tau will also will be equal to 0, that is what we have seen. The second part is that a black body, already I said, is a perfect emitter. Okay? That means, the emissive power of a black body is taken to be the unity, that is that is the highest emitter. So, no other surface can emit more than a black body, okay, at the same temperature. So, therefore, the emissivity epsilon is equal to 1.0 for black body. Okay. And then the another part is that emission from a black body occurs in all possible directions. Now, emissions from a black body occurs in all possible directions. Okay. So, we can say a black body is a perfectly diffuse emitter. Okay. Now, so it is expected or it is understandable that or many a times we see that a surface which is black is called to be black body. The idea is not that. Idea is that a black body means it will absorb all the radiation into itself, incident into it should be absorbed. Okay, that is the main thing, and therefore, if there is no visible frequency comes out from that, then it looks like a black body or black substance. Now, what happens is there can be some white substances which are also black with respect to some radiations. So, it is not that we are thinking about the visible ranges, that there can be some substances which are black with respect to other thermal radiation range. For example, milk appears white, it appears white to our eye, but it is black to long wavelength thermal radiations. To some. So, with respect to those wavelengths, it is black. Similarly, snow or ice, they have also similar kind of things. With respect to some wavelength, okay, they are black. Snow or ice also black. Though they look white, they are black with respect to some wavelength. So, this whether a body is black or not, black body or not, it depends upon that some kind of subjectivity is involved into this, that how much wavelength, to what extent of the range of the wavelength we are considering. But when we say about in normal situation a body is black means that in the visible range colors we have 7 colors VFG, all these colors, if the color frequencies, if a body absorbs, then naturally it will be looking like a black, and then we call it to be black body in the visible range of thermal radiation. Now, another point also should say that when we have say a cavity with a small aperture, okay, and some radiation is incident into this. So, this is a cavity. So, with a small aperture, the incident radiation is coming into this, and incidence falls, then it gets reflected in different ways, they get reflected. Okay. So, it is falling and then getting reflected in different ways depending upon the kind of these things, and while doing these reflections, several reflections are being happening, and by the process it gets absorbed, the whole material gets absorbed. Then this cavity will become like a will behave like a black body. Okay. Provided all the incident radiation whatever is going through the aperture is getting absorbed, and this aperture means fine aperture means the incident radiation will be of a limited wavelength range, and this wavelength range waves will be getting finally absorbed into the body, and it will not be further emitted. So, it will look like it will behave like a black body. Okay. Now, yes, we have to discuss something on some important laws related to the radiation. The first one is, so there are several laws we will be discussing. One is the Plancks Law. So, according to the Plancks Law, it says that the emissive power, of a black body is a function of the wavelength. In fact, at a given temperature, a body can emit radiation of different wavelengths. So, it is a varying wavelength, it can emit energy. So, therefore, there is a terminology called monochromatic emissive power. It is also called as spectral So, what is this? Emissive power means is the amount of energy, radiation energy emitted by a surface per unit area per unit time. So, if I say emissive power, normal emissive power, it is also called as hemispherical emissive power. Hemispherical means the surface is there and it is covered by a kind of hemisphere. So, all ranges of all the directions are being covered in these, and this is called hemispherical emissive power. This is say EB, and it is given as the amount of radiation energy emitted by a surface per unit area per unit time. And therefore, what happens is that unit of EB, emissive power, and this is B indicates black body. So, we are telling about the black body emission. So, for emissive power of the black body, and the unit of will be equal to watt per meter square. Watt means joule per second. So, that is it is the time is taken care of in this. And in case of monochromatic emissive power, it is represented as say EB lambda for a wavelength lambda, especially for the wavelength lambda, and its unit is watt per meter square per micrometer. Micrometer is the wavelength. So, it is that per unit wavelength, emissive power per unit area per unit time per unit wavelength, that is called monochromatic emissive power. And according to Plancks law, okay. Now, EB lambda, this monochromatic emissive power is twice pi h c square lambda to the power minus 5 by exponential h c by lambda kt small kt minus 1. Okay. And here this also can be written as in a different way, lambda to the power minus 5 by exponential K2 by lambda t minus 1. Here this also can be written as u lambda into c by 4. Okay. Now, here K1 is equal to twice pi c square h, K2 is equal to h c by small k, and u lambda is equal to 8 pi h c lambda to the power minus 5 by exponential h c by lambda k t minus 1. Okay. Here c is velocity of light, and it is, we know that 3 into 10 to the power 8 meter per second. Then h is equal to Planck's constant, and we know this value 6.6256 into 10 to the power minus 34 joule second. Okay. Then k is, small k is Boltzmann constant, and this is 1.38066 into 10 to the power minus 23 joule per Kelvin per molecule, and K1, capital K1 is equal to 3.743 into 10 to the power 8 watt into micrometer to the power 4 divided by meter square, and capital K2 is equal to 1.4387 into 10 to the power 4 micrometer per Kelvin. Lambda is wavelength, it is in micrometer. T is absolute temperature, that is in Kelvin, and u lambda is called energy density of radiation. Radiation per unit volume per unit wavelength. Okay. Now, at any temperature, a black body emits radiation covering wide range of temperature. So at any temperature, the hemispherical emissive power of the black body, that means it is covering the whole range of wavelengths, that means covering whole range of wavelength. We have E b is the hemispherical emissive power, and that will be equal to, we have to do the integration 0 to infinity E b lambda and d lambda, and that is equal to 0 to infinity k 1 lambda to the power minus 5 by exponential k 2 by lambda t minus 1 d lambda, and this after integration gives us sigma t to the power 4. So, there are some references from where the integration can be seen, and here that sigma is basically pi to the power 4 by 15 capital K 1 by capital K 2 to the power 4, and here it is t to the power 4. So, this is the expression for sigma, and we know that sigma is called Stefan Boltzmann constant, and its value is equal to 5.669 into 10 to the power minus 8 watt per meter square per Kelvin to the power 4, where T in Kelvin. Okay. Now, another thing I should discuss is this Wien's displacement law. So, we have seen the Stefan Boltzmann law. Stefan Boltzmann law says that E b is equal to, according to Stefan Boltzmann, E b is equal to sigma t to the power 4, that already we have discussed. And then coming to Wien's displacement law, it says that lambda max into T is constant, and that value is 2898 micrometer Kelvin. So, what that means? Lambda max. So, what happens is at any temperature a surface that gives with different temperature, it gives it radiates of different wavelengths. So, this is that for the varying wavelength lambda, and here it is, this is E b lambda. So, any surface or a surface that emits some radiations, that is the emissive power, that is a function of lambda. So, for different values of so it emits radiation of different values of lambda, a surface at a particular temperature, and say suppose this is the temperature. This temperature says that it is the emissive power, for this lambda, and so this lambda will say as to be lambda max. So, that is that emissive power of the surface at a particular temperature gives us this lambda max value, that is the maximum wavelength which gives a maximum emissive power. So, this is the wavelength lambda max corresponding to maximum emissive power, and this lambda max multiplied by the temperature at which this is happening, this product gives a constant value. It is called 2898 micrometer Kelvin. So, this is called Wien's displacement law. Why it is called displacement law? It says that if we change the temperature, so if I increase, if I do it at say suppose if I say this is at a temperature T1, and if we have something at a temperature say T2, I am sorry, so this is suppose this is a temperature T2, and this the maximum is happening at some. So, here it was say lambda 1, and this is happening at lambda 2. So, if temperature T2 is greater than T1, then lambda 2 will be less than lambda 1. That means, at higher temperature the maximum will be obtained at a lower lambda, and at lower temperature the maximum will be obtained at a higher lambda emissive power. Therefore, the lambda max into T, that this is lambda max again with respect to temperature T1 at lambda 1 at lambda 2. So, T2 into lambda 2 will be equal to, so T2 into lambda 2 will be equal to T1 into lambda 1 is equal to T into lambda max, and that is equal to 2898 and micrometer Kelvin, and that is equal to constant. So, this is why it is called displacement law. So, if we increase the temperature, lambda will be displaced to the lower region. If we decrease the temperature, then if we say this here, that this is here, this is a lambda 3, here T3. So, T3 is smaller than T1, and then lambda 3 is greater than lambda 1. So, it will be going to the other side. That is why it is called displacement, Wien's displacement law. The fraction of or the radiant energy, the fraction of radiant energy between two wavelengths can be obtained from E b lambda 1 to lambda 2 by E b 0 to lambda, that means the whole range, and this E b 0 to lambda is equal to, this is equal to sigma T to the power 4 as per Stefan-Boltzmann law, and that will be equal to we can get E b 0 to lambda 2 by E b 0 to infinity minus E b 0 to lambda 1 by E b 0 to infinity. So, this way we can find out the values of lambdas. Now, the next part which is left with us is the Kirchhoffs law. Now, according to the Kirchhoffs law, for a black body, alpha is equal to epsilon. So, emissivity is equal to absorptivity. Now, this can be proved like this. Say we consider an enclosure, and there is a small sample here. This enclosure, large enclosure, and this is a small sample. at thermal equilibrium with the enclosure. So, enclosure is say it behaves like a black body. So, then what happens is that energy emitted by the enclosure, which say which is incident on the sample of say area say A1. A sample here I will say small sample, I will tell is the body 1, okay, area A1. So, this is body 1, here area is equal to A1, then that is equal to say q dot. So, q dot is the energy that is coming from here, it is incident on it. Now, alpha 1 is the absorptivity, of body 1, then alpha 1 q dot into A1, that will be equal to the energy absorbed by body 1. So, we can say that this is q dot, this is also a flux, we can say this is a flux, that means per unit area. Q dot is amount of energy coming per unit area per unit time. So, q dot is that flux into area is the total energy, and into alpha 1 is the absorbed by body. And under thermal equilibrium, E1 A1 is the energy emitted by body 1, and that will be equal to q dot alpha 1 A1. So, E1 is the emissive power of the body 1. So, under that situation we can say now, if the body 1 is black, then EB1 will be equal to q dot, because then alpha 1 will be equal to 1.0 and area cancels. Okay. Then what happens is, we can say that alpha 1 is equal to E1 by EB, and we know that from definition E1 by EB is called emissivity. Of body 1. So, that means alpha 1 is equal to epsilon 1, that means a body under thermal equilibrium with the surroundings or the large enclosure, as you said, then its emissivity will be equal to absorptivity. Now, the question is that Kirchhoffs law is valid when? So, Kirchhoffs law is valid for thermal equilibrium, but in general what happens is, in general the emissivity is a weak function of temperature. So, therefore, temperature and wavelength. So, Kirchhoffs law is applicable when source temperature is of irradiation is equal to the temperature of the irradiated surface. Now, so for all practical purposes, as I said that emissivity is very insensitive to temperature change and wavelength. All practical purposes, epsilon and alpha of surfaces are nearly equal even if the temperature even if the thermal equilibrium does not exist. So, therefore, now a new terminology has come, that is called gray body. So, gray body is a body which is a substance, it is a substance whose emissivity and absorptivity are independent of wavelength, whose emissivity, right. So, alpha, epsilon emissivity and alpha are independent of wavelength. So, what happens is, as we have discussed, that epsilon is equal to alpha, that is the Kirchhoffs law, emissivity is equal to absorptivity. It is valid for a particular wavelength and for black bodies, and we have seen that emissivity is not much emissivity is not very sensitive to temperature and wavelength, and therefore, that epsilon and alpha can be even for any other surfaces which are not in thermal equilibrium can also be taken to be the same, and therefore, a new body concept has come, which is basically a substance whose emissivity and absorptivity are independent of wavelength. So, the gray body is an ideal body with, so gray body is also a kind of ideal body with epsilon and alpha are less than 1.0, and ideal body is the black body whose epsilon and alpha is equal to 1. So, for gray body, so E epsilon emissivity and alpha absorptivity are less than 1. Okay. So, now if I say a small problem that a black body has a total emissive power, or say has EB equal to 6 kilowatt per meter square, then what would be the surface temperature and the wavelength of maximum emission, that is lambda max. So, the question is this. So, the answer is that EB equals to 6000 watt per meter square, and that should be equal to 5.669 into 10 to the power minus 8 t to the power 4 sigma t to the power Stefan Boltzmann law. We know that EB is equal to sigma t to the power 4. Then we will get T is equal to 570.4 Kelvin, and then the lambda max into T is equal to constant, that is the Wien's displacement law, and from here we can get that lambda max will be equal to 2898 by 570.4, and this value is equal to 5.08 micrometer. So, this is lying in the infrared region. So, this wavelength lies in the infrared region. Okay. So, this is all for this lecture. In the next lecture, we will be discussing on that radiation intensity and and radiation view factor. Thank you very much.